Thank you. So hello, my name is Shaun Smith. I'm a product manager with the Serverless team. So I lead the team at Oracle. And we're building a cloud service for serverless. And we're also doing some open source work I'll talk about. And the topic of the talk is, is Java the right thing for doing serverless programming? So I'll talk about what's serverless, but look at the problems that Java has, and the things that we've done to get over that, like the triumphs. I don't know if it's triumphs yet, maybe it's successes. The things we're doing in Java, things Java is doing to make themselves suitable for a new kind of runtime environment, not like we're used to in traditional. So I do work for Oracle, so I'm just going to say, if I say something about a product, don't buy a product based on what I say. It's future stuff. So I'm talking about the future a little bit. Okay, that's it for Oracle. Okay, so just to start off with, what is serverless? So serverless is not one thing. Serverless is a broad category of services. So anything where you're not managing infrastructure is serverless. So in some ways, Gmail is serverless, right? No one provisions the server when they get a Gmail account, right? So it's SaaS applications. All those SaaS applications are essentially serverless applications. But in terms of a set of services that are serverless, where you don't provision infrastructure yourself, functions as a service, or FaaS, is the compute component. So you're building these services. It's a serverless compute environment. You're not going to deploy. You're going to deploy your applications or your functions. You're not going to provision hardware. The server is completely under the covers, right? So it's gone. So I'll explain what I'm talking about here. So the model for function programming is you have a piece of code that takes an input and produces output and may have some side effects. So this is essentially like a microservice, except that there's only one entry point. So today you may use Spring Boot or something, you spin up a REST API and you deploy it on something. It has multiple endpoints, multiple entry points into your application. In a functions world, there's only one way in. Okay, so they do one thing. So as a banking application, you'd have debit function, credit function, transfer function, but they're all separate. And the goal, of course, is that these are small units of work, small amounts of code that you can edit, you can understand, you can debug it, you can code review with your colleague. They're small enough to comprehend. So this is sort of the promise of functions, is they're small enough for us to fit in our heads. Right? Kind of like the idea of why we would decompose classes into methods. We want smaller chunks of logic or algorithms that we can understand. So functions are designed to be very small, simple as possible. They can get complicated. And with input output, now they may have side effects, like I say. So they may update a database, they might interact with storage or event queues. That's fine too. So some of them may not actually have the output. They're simple things. And so your application would be a collection, right? So you're building applications. You're building, if you're banking, right? Debit, credit, transfer. All these features of your system get exposed or built as small functions. So your application is a collection of functions. So why is this a good idea? I'm sure there are many people who think it's a bad idea, but the basic idea of serverless, which is you don't think about the infrastructure. So today, if you're doing Java E development in the cloud, you typically have to get an app server started, boot it up somewhere, possibly some infrastructure, a VM, install the operating system, patch the operating system, patch the JDK when new versions come out, on it goes, right? You're constantly doing that. In a serverless world, you don't do this, because you don't see servers, you don't see hardware, you don't see any of that. It's transparent that there's compute. Of course there's compute, but there's transparent compute. Sorry, my phone's ringing. And behind the scenes, the big promise is scalability. I'll talk about scalability in a moment, but scaling is a big feature for serverless function platforms, and how we can provide limitless scaling or high degree scaling. There's some questions around speed. So of course, writing smaller things is easier to do. You should be able to write a small piece of code, write tests, unit test it, iterate on that, put out a version, put out a new version. You hear this a lot in the microservices world. Netflix is famous for talking about how they deploy new microservices every day during the day. They have thousands of microservices. They're deploying it a whole bunch. Functions is the same idea, except they're smaller. So I've taken a microservice and I sliced it into smaller parts. Same rules apply about iteration. And uniquely for functions, you only pay typically when your function is running. Okay, so if I can deploy 1,000 functions to a cloud server, to a FAS, Functions as a Service Platform, I don't pay unless it runs. It's sitting there doing nothing. If someone invokes the function, then the metering begins, right? So how much compute is it using, how much network, whatever the measure of the provider is, you only pay for use, which really makes it suitable for a lot of interesting kinds of workloads, different kinds of workloads than maybe you would have thought of before. Right? And we'll dig into a few things. So this is kind of a joke slide, but there are servers, right? Serverless is totally a point of view. The provider of a cloud service, whether you're Amazon or Microsoft or Oracle, whoever, you've got tons of servers and there's a lot of them. It's a bunch of work. That's what our team does, right? We're managing a whole bunch of servers, figuring out how to place workloads on servers for you when you deploy your code, so you don't have to do it. You patch the operating system, you do all that stuff that you don't want to do. So from our perspective, this serverless function platform is entirely full of servers. From the user's perspective, it's completely serverless. Now, the name serverless isn't very good, and there's even a series of conferences called JeffConf. Jeff was just the guy, they said, serverless is a dumb name, we can call this conference anything. So they called it Jeff. And they had a few of those in London and around, and now they've changed it to serverless days. They kind of gave in. They were being cute, but you know, even if it isn't an accurate name, it's a name. Right? So anyway. The no server thing, the serverless thing is, like I said, a bit of a joke. Someone posted on Medium that they had ported the FN project, so the thing I work on, FN, to Raspberry Pi. They basically got running on ARM, and they were doing, I think, home automation. And the first quote was, "That is clearly not serverless. I can see the servers in the picture." Yeah, okay, fine, right? But someone's got to do it. It's a dirty job. Someone's got to own the server. So this poor guy has this thing built. His users, of course, it's serverless. They're deploying some functions. They don't know it's a Raspberry Pi. They don't know how many there are. They don't know anything about this. So it's a running joke, but serverless is maybe not the best one. I'm from Canada. I live in Toronto today these days, so I have a hockey stick for my metaphor, of course. So this is where I'm going to talk about the scale. So the real promise of these function platforms is scalability. So let's say you have a function deployed and some service. So you have a, my favorite example is I have an Instagram filter. So I have a function that takes an image and puts on puppy dog ears and then returns you back this nice cute picture with a puppy dog ears, right? And I read it for my children's day, so they love it. They think it's great. They tell their friends. Right? It's running on the cloud somewhere and their friends are calling it. It's getting more and more usage. They're telling their friends in school. Right? So this thing gets called more and more and more. And so what's happening behind the scenes is the cloud, the FAS platform is actually instantiating more and more of these functions. There are more and more of them running at the same time, concurrently, handling the workload. Now, let's say that at some point, popularity increases and someone posts on Reddit that I have this really cool function. And suddenly I get the Reddit bump. I get this, crazy inflection point. And I've got thousands and thousands of people calling this. So the question is there a problem? Well, no. So for me, as the developer of the function, I have built something that takes input, does some processing, and produces output. So if I have 1 or 10 or 1,000 of them, it doesn't matter. Right? I'm not having to manage concurrency. They're very standalone. So it's possible to have more of them. It doesn't matter to me. As a programmer, I don't have to worry about these things, which is a nice part of the model. The second thing is, the cloud provider, or the FAS provider, it's their job to make sure there is resources to handle this. And this is their job. That's part of what they do for a living, right? What we're doing for a living. And this curve here is really important. This is something that a lot of companies plan for all year. So there's big retailers in the US. In the US, again, I'm not American, so I'm a foreigner as far as they're concerned. They have Thanksgiving, American Thanksgiving in November. In Canada, we have it in October, like it's supposed to be. It's the harvest, right? So we celebrate the harvest. So we don't do it in November. It's winter. Anyway, so they have this thing in November, they have this Thanksgiving, and they have sales, right? They have Black Friday, and they have Cyber Monday. And companies, big companies I've worked with, they spend all year worrying about this, that when that day comes, they will have compute to handle this thing. Which means they also have to have compute all year, so they're wasting a lot of money, right? So their OpEx is, their capital cost typically is terrible. They're buying computers to handle their worst case, which only happens once a year. Pretty bad. these function platforms let you basically pay for what you use, and when it gets really bad and spikes up, you're paying for it, but you're not paying for it all year. So this is kind of the problems of these platforms. So which brings us to, so what's the state of the world right now? Or at least in the last year or so. Where is serverless? Well, there's a lot of hype, right? So, and you know, the magazines, right? So the hype. Serverless is eating the stack and people are freaking out. AWS Lambda has now deprecated on containers. So clearly containers are dead. I don't have a date on this one, but they decided containers are dead, functions have killed them. This one's even better. You know, serverless adoption on par with containers. So who here is using containers? Okay, and who's using functions? Okay, one. Okay, so the odds are they're not on par. Okay, so this is a complete lie. That's last year. That's last August. So maybe, you know, they're excited. This is a quote. This is Chad Aramura. He's a VP at Oracle in my team. And he was talking to an analyst company, one of the big analyst firms, and they said, so he's quoting here, right? Interest in serverless functions from our customers has ranged from astronomical to outrageous. So customers are talking to analysts saying, tell us all about functions because we think it's really hot, because they read those magazines, right? They read that article. So there's a lot of hype going on right now. So I would say we're kind of on the hype cycle. We're up there somewhere. I think it's cooling off a little bit, but you know, we're in the phase of this new thing is the thing that solves all our problems, and all the old stuff is crap. Right? That's how people are. Right? We want the new shiny thing. So everyone's like, functions are cool, containers, they're the best. But we're heading down this hill to here, where we'll be going, well, the containers suck, these functions suck. We tried them, they didn't solve all our problems, they're clearly no good. And then we're going to eventually move to reality, which is, it's just another piece of your toolkit. Right? So functions are another way to deploy some code. It's not right for everything, it's good for some things, and it's going to be part of your mix of services. So that whole business of like scale on demand makes it really good for things that come and go, things that don't run 24/7. So if you have services you're providing to your customers that run 24/7 and they're loaded all the time, functions are not a good idea. Because typically, they're slightly more expensive, they'll be more expensive than just running, say, a microservice. But if your service doesn't run 24/7, if it runs intermittently, you have to really do the math. If you pay when it's called, that could be cheaper for you. And if you have this very peaky kind of workloads, where provisioning all to handle the high peak is more expensive than just letting using functions are good. So there's no perfect solution for when to use them, but it's just going to be part of the mix. Okay, so functions is another new thing, and next year there'll be something else. But they're really nice, but they're one thing in the toolkit. Which brings us to Java. So, okay, well, serverless is hyped. What's the story with Java? Well, you've all seen this, right? The Red Monk language ratings. We all love this, you know, because it's like we look for our favorite languages and see if we're cool. The ones I like are sliding down to the bottom corner. But Java is, hooray, up here. But it's way up in there. I got a magnifying glass on. Java, JavaScript, Python, and a few things in there. So Java is one of the top languages, right? Used by, I think I saw an article today, and said like 14 million people are programming in Java. It's a good number. Right? So it's really popular. So it's pretty dominant. In functions, that's not true. So according to the Serverless.com, which is a company who offers a framework for trying to smooth out differences between different providers' platforms, I'll give you a generic API. These guys keep track of stats, so it's not scientific. It's their experience. If you look at these numbers, nodes got about, between node 4 and 6, this is like last year, all those 2018 numbers. That's 75% of all functions are written in Java. JavaScript. The poor little Java here is 4.96% of Java. So in this space, people are not using Java. They just aren't, right? Not really. And if you look at the trend, that's also no friend to us either. So Node is going down. Node 4 anyway is going down. I don't know where Node 6 went, because you think it would be going up. Python, as expected, 3 is going up, 2 goes down, and Java's kind of just steady state. So Java's not making any ground. So of course the question is, why is this the case? Right? Why is it that this dominant programming language that we're all using, we're all like, oh, Java's awesome, is not being used in this space very much? So that's the question. So it's the question and sort of the challenge for us. So if you look at Java's usage, Lambda, which is the first major cloud platform to give a functions platform, and there are other people, but they're the big guys, right? Launched in November 2014, put out Java some month later, 7 months later or so. That means it's been out for 3 years, and it's still, probably 5%. So the serverless.com people don't run their own platform. They deploy code to other people's platforms. So we're talking about numbers of people deploying to Azure, to Amazon, and different platforms. So they do include Lambda numbers in those stats we saw. So Java's not that great after 3 years of being available on a major platform. Python and Node are really popular. And the question is, why is this the case? Is it because people are using functions as kind of a scripting for the cloud? It's a little place to put a bit of code. Something happens, like someone puts something in a storage bucket, and they're going to run a little script, and they're thinking scripty, and they think, oh, Node's good for that, or Python's good for a quick script. Right? Not really industrial, commercial thinking, but more about a quick hack. Maybe the first people using this had simpler use cases. I don't know if that's possible. If you're an enterprise, you have complicated use cases. The last two are really good questions. Does Java development not fit the style that people have or used to with building functions? What's been provided so far? And is the JVM a problem? Because one of the things with these functions is, and there's all kinds of optimizations, but really they don't necessarily live that long. So they start up, they do something, and they quit. Or they start up, and they handle a few requests, and then they're taken down. And then, because of course, you don't pay when it's not running, and cloud providers will probably cache a few things. People build FASs. At some point, we're going to take it down to free up the capacity so that some other function can run. So if you call a function at point A, and then it's idle for some time, at some point it will be gone. If you call it again, you have to start up the function, which if it's Java, starts the JVM. Right? So there's a cost. So latency is an issue. So there are real challenges. So we'll dig into these. So the question we have for ourselves is, James Governor had this article, we all heard this, when web companies grow up and turn into Java shops. So large enterprises, Twitter and different people were using other things besides Java. When they started, but Facebook, whatnot, by the time they become really serious enterprises, they move to Java for reliability, scalability, all kinds of good reasons, right? Reasons for all moving to Java. The question is Java the language for everyone, for everything, right? So, when function companies grow up, do they turn into Java shops? It's kind of the existential question. I think it's possible. We'll look at some of the reasons here. So for Java to be useful for functions, I think there's a few criteria we have to solve. First off, I think it has to be plain Java. So people like to program in Java. They want to program in plain old Java. They don't want a subset of Java or some sort of cloud version of Java. They want a scriptable Java. They want Java. Okay, so we want to make sure we have support for plain Java. And this thing about the question before was sort of, does it fit in with the development experience of other people building for the cloud? We want good tooling, right? So if you had to use some special tool to deploy your code to some certain FAS platform, that would suck. So we want good tooling, wide range of tooling. And I want to build complicated apps. So far we've talked about functions as these little standalone units of work. But really that's not an application, right? An application, you're composing together a functionality to build higher level services. So there needs to be an easy way to combine them together. And the last thing is this low latency, right? So Java, we have to have low latency. Java has to start fast, has to run fast, because of this environment it's in. It's no longer in a world where I'm running app servers for 3 months. I've had customers who I think running for like a year before they rebooted. They discovered at the end of a year that their logs were messed up, so they didn't have logs for it. But it's probably good to reboot your system, but the JVM has been tuned for long-running processes that incrementally compile, hotspot, all that kind of stuff is great for long running. So now the question is what happens in this short-lived function mode. So I'm going to talk in the context of Java in general, and then use the FN project I'm working on as an example, because we have really good support for Java. We'll see what it looks like, and we'll see we'll see how it works within the context of FFN. Anyway, some of the questions I can answer in general, some of the answers are general, some of them are solved particularly by FN in terms of what we're trying to achieve here for Java. So FN, it's open source, it's on GitHub, it's Apache 2, so anyone can use it, very permissive license. I'm going to run it on my laptop today. You can run it anywhere. Apparently, you can run it on Raspberry Pis because we saw the guy did it. Cloud, so Oracle, I'm building Oracle Functions Cloud Service. So I'm building a service version of this thing. Our goal is to have the same bits running on your laptop, running in the cloud, so you know that when you deploy your code, it's the same infrastructure, right? So you're going to the same experience. We have really good Java support, so which is a reason why I'm going to talk about Java. So we're really Java is probably our best supported language. I think it's because I have a bunch of people in Bristol in the UK who really know Java really well, and so they've built really excellent support. And something you need to know about FN is that functions are Docker containers. So we package functions as Docker containers and deploy them. So that's how we package up your code. That's how we run this code, right? So when you're running a function on FN, it's running a JVM inside of a Docker container with a certain contract for like how it receives input and return output. Okay, so this is we're not the only ones who think this is a good idea. This is Kelsey Hightower. He's a guru of the serverless world. Like, everyone follows Kelsey Hightower. Does it have his followers on there? No, it doesn't have it. He's going to be high. At least within the serverless world, he's a micro celebrity. Right? So Kelsey Hightower is saying, yeah, he's looked at a bunch of things. He thinks the serverless platforms. He gets the point in dealing with source code. So some of them, you go on the web and you type in some function code and you can save that it deploys your code. That's great for demos. Okay, but the real world, you've got Git and you've got lots of code. He believes, as we do, you should take your code, build containers, and deploy those containers. And that's your function. So we believe that we're on the right track, and we think that Kelsey's given us his endorsement, I guess, in a way, without knowing it. So let's look at FN and Java, right? What can we do here? So what I'm going to do is just introduce the support. I'll give you a demo. I'll just go to code. So for each language we support, we actually do support more than Java on FN. We're supporting Java, Node, Python, Go, and Ruby. Ruby's kind of like the last one in our list of supported languages. We're trying to add the full five. You can deploy anything on FN, anything as a function, it turns out, but we have specific support for those 5 languages. For Java, we have this FDK. We have a Ruby FDK and a Go FDK, and so on. We have a Java library, so an API that the applications can use. We've got JUnit testing support, we have a JUnit rule. We have a build with all the tools. So when you're building with FN, you can actually not have Java installed. You can actually create a function, write the source in text editor, I guess, and actually build and compile. So we have a Docker image within the build that contains Maven, Java-C, and all the build tools. And then what we do is we take that, we build in one image, and take the results, which are you produce, and put it in a smaller image for runtime. So we'll talk about that later. Like small Docker image is important. So we want small images that just contain enough runtime to run your Java application. So this is sort of a set of things. So each language we have this. We have some Docker containers for build, running, and libraries. So let me just show code to be more clear. So I've got an FN server running here. I'll just Control C this here. Okay, so I can say I have a little command line utility called FN. This is our CLI. I can say FN start, and for a local developer, you can say start, and it'll start the server instance up, which is itself just running in a Docker container. So I started a server, it's version 3.5.7.4, up and running. Okay. Great. We're on a different shell here. And here it is up here. So what I can do is, and create a new function. We have support for building a new function. You don't have to use these little helper utilities, but it's good for getting started. You can say init, runtime is Java, and I'm going to call this hello. Okay, it's just hello world application. So I've now got a folder called hello. So what we do is we put functions in folders with the same name. So we have a coding by convention. So we have lots of functions, they all have a folder that contains them, and their name of the folder is the function name. So I'm going to hello. And you'll see here, this looks very boringly Java, right? So I've got a POM, source folder. I got a POM, source folder, I've got a function, I've got a test for that function, and I've got this metadata file func.yaml, which is our metadata. So I'll take a little tour through here and you can see what it looks like. If you find it underwhelmingly dull, that's good, because the whole goal here is that this should not be special, right? So this is just be Java. So once you see this code, you should go, wow, that's pretty boring, in a good way. So here's a function. Okay. There's nothing in here to say it's a function. You can't tell, right? So it's just a Java application, a func class, has a method. The name isn't important. In this case, we call handle request. This is the body of the function. It takes a string. It does a check on if it's null or not, and decides, does it go hello world, hello name, or hello world by default. Returns a string. Takes a string, returns a string. Nothing special. Okay. I can run that code. So let me show you I'll show you the func YAML file. Func YAML file here is our metadata. It tells us the name of the function is hello, version of that function, the runtime we're using, and these are the build images. This is the image we use to compile, has Maven in there. This is a smaller image we have. It's Java 9 also, that's going to be more compact. And we declare that this class is the function class, and this is the method that is the function. Right, so I can call this anything, so there's nothing special about the names, it's just declared. So that when we run this function, or build this function, we use this file to know, okay, this is the class that's basically going to be called when we invoke the function. So why don't I just run this? And I'll do it, I'll do verbose mode, do build. Okay, I do verbose mode so you can see what's happening. In here you're seeing, if you're a Docker savvy person, you're seeing a Docker file running. Of course, Maven. I'll use that, okay. But you're seeing Docker file commands go by. So what's happening is behind the scenes, we're actually generating a Docker file on the fly that will build that function into a container. It's pretty deterministic how we do it. We do it behind the scenes. If I do it again and Control Z this, you'll see there's a Docker file up here in the file system. So we've actually generated this on the fly. It does what I said. It does compile, gets the dependencies, packages all up, builds the jar, and then copies the jar over into another image and tells us how to enter it. So it's all pretty. If you're a Docker person, this is pretty vanilla stuff. Finished. Okay. So we've got this thing built. I can go fn run. Okay, and call it. What I've really done here is I've done like a Docker run. Right, so there's nothing very magical. I've got an image here even. Right? So my image, so if I do a Docker images, let me grab the hello there. Okay, so I just create that Docker image. It's 394 meg. Yeah. Okay.
How big is the last layer?
What's the layer from that? It's minute. Yeah, the last layer is not going to be big. It's not going to be big because
that's the key, right?
Well, no, not necessarily. I want the whole thing small. So we'll talk about that. Yeah, that's big. Okay, I can get it to a tiny fraction of that. I'll get there. So anyway, but the point is, it's there. It works. I can do a deploy. So I can go fn deploy. The app, will call it Berlin. And I'm going to say local, which means we're dealing with Docker here, and deploying is really pushing container images. So if I say local, it doesn't push the Docker hub. Okay, it just saves me a round trip. I'm just going to keep it on the local machine. Okay, so I deploy the function. Now if I say fn call, actually invoke, we're actively developing this project. So we're changing our CLI, so if I slip out this, because I'm using the old command. Invoke the function, it's the Berlin application, and we group functions into applications, it's really just a namespace. So invoke the function Berlin, it's hello, right? You see there's a bit of a pause there, okay? If I call it again, it's fast. Right? So that's an interesting thing right there. So if you look at the log for the server, here it says hot function launcher starting. So what we do is when we start a, actually let me flip over here if I do, here it is. Docker, yes. Oh, I have all kinds of stuff right in here. Oh, there it is. So I have my container. That function is running. So what happens is we start the container up, function container, and we can call it repeatedly. It can stay alive. We can have it handling multiple requests. So the cost that I pay for booting that JVM happens one time, except that this will get basically timed out. So if I look again now, if I do Docker PS again, it's going to be gone. It's gone, and over in the server log, I can see what function terminated over here. So it's being taken down. So let's see here. If I time that, if I run this thing and time it, you'll see there's a significant difference. Okay, so it took almost a second. You do it again, it drops a lot, right? Because now I've got a JVM booted, and a container booted. So I'll dig into this. This is an issue for how this works. But anyway, you've seen basic Java. Let me show you that it's a bit more sophisticated than that. I didn't show you the test, but I'll show you the test. I have another one here. Oops. Yeah. I've got another function here which is almost the same, but rather than taking strings, I'm passing in objects. Okay, so close this over here. So similar kind of thing, except that this object takes an input object, which is an object with one property, and it returns a result object, which is another object with one property. So I'm passing in complex objects. And so the FDK, when you tell it, hey, this is basically my function, it can introspect the signature of that function, understand the types required, and by default, and this is overrideable of course, but by default, if you're passing in a complex object at a POJO, we will assume you're going to be passing in JSON. And if you're passing in JSON, we will use Jackson to unmarshal the incoming payload you're passing in into one of these instances of these objects, pass it into here. It'll do whatever it does. It will pass out a result object. We will take it and we will unmarshal that into, or marshal it into JSON using Jackson. You can come in and put Jackson annotations on here. You can even swap out the marshaller altogether. Use whatever you like, not Jackson. JSON, you can use XML, your own proprietary format. It's all plugged in. But there's a lot more going on behind the scenes than is initially apparent. Right? It's much more clever than it appears. Just to show you the test. I didn't show you the test before. This is a test with the POJO, so there are some imports that say FN project now because we have JUnit libraries. Here's a simple test. Create a testing rule instance. I can go and I can create an instance of the function, and I'm going to invoke it with a body. So I'm going to pass in a payload. So it's like an object. Remember, it's an object with a name property, so Tom. I'm going to queue that up, and I'm going to invoke the function, so fire it. And then I'm going to get the result out, and then I'm going to do some assertions on the results. So I can write nice JUnit. I can run from here. Right, so it runs the test. It's all green, it's all good. So I'm using my basic typical tools, right? Some IDE, doesn't really matter what it is. It's got Maven support. It does a parse, and then give you code assist on Java. That's basic tools. So there's nothing special, right? Nothing special going on. At least it doesn't look like special going on. Okay. Let me go back over here. Okay, so what we saw was plain old Java, right? That was just really plain Java. We weren't even any annotations or anything in there, it's just Java code. All you need to do is know where to go. Whatever tools you want, it's great. Your choice, right? It's just Java. Kind of simple, right? Next things I wanted to be able to do with functions with Java is build complicated applications. This is getting more interesting. And this is where I think the functions development, or the people who are building FAS platforms are at now. We're all trying to figure out how do you build applications. So we've got something here called FN Flow, we'll talk about. Microsoft has gerbil functions it's kind of similar. Actually, they're on the same wavelength as we are, I think. IBM has a thing called Composer, which lets you sort of visually draw pictures of the functions called functions with some sort of data flow. But we're all at this phase now. We're going from functions are run when an event occurs and we do something. That's the phase generation 1 of functions. Now we're on to phase 2, or generation 2, which is I'm going to build apps out of functions. So Flow lets you basically describe your algorithm you're going to do with multiple functions in code. So rather than, we felt that if you're a Java developer and you're comfortable with Java, why would you learn another language or technology to just describe an algorithm? Function A calls B calls C, and if an exception occurs, then something happens. We know how to write that in Java. We thought that was the right way to go. So there are platforms like Amazon Step Function or Amazon Step Functions, which are YAML-based descriptions of flows. Essentially, it's a workflow. We're not worried about workflow. We're talking about algorithms. Right? We're at the code level. So we're going to describe how to build apps with code. It's going to get all the advantages of being built on the FAS, so it'll scale up and whatnot. When you're dealing with functions, you're inherently building distributed programs, right? So you've got this compute fabric, and all these functions are independent containers running everywhere. So you've got this distributed programming model. You may not notice. It does start to come out and start building applications now. And so Flow supports a lot of concurrency primitives. So, fork join, fan out, fan in, exception handle, that kind of stuff. I'm going to just walk you through it. So the way it works is we basically started with Java 8 completable features. So has anyone used completable features? Yeah, okay. That's more than most groups. We thought we will choose the most popular framework and implement and work with that, but then no one knows what it is. No, it's pretty good. So completable features is it's a features or a promise API. You can get a handle on the value of a computation that is incomplete. So you say, I want to do some computation, and this feature will hold the result eventually. In the meantime, I can pass it around, I can do things with it. Completable features is designed for managing threads. Okay, so it's built on, actually I think I'm going to say this here. I'll get to Lambda in a sec. So it's built on it's part of the Java util concurrent. It uses the fork join pool, so this is running threads in a JVM. Our problem is that we're running processes across a bunch of compute nodes, right? Containers across a bunch of machines. And so what we did was, we actually worked with Brian Getz to get some guidance on this, but the completable features framework in Java util concurrent is not extensible. So it's basically a single implementation. We implemented something that looks a heck of a lot just like the real one, but with some extensions for doing functions. So it has a few extra parameters here and there. Basically, it looks the same. And it lets us deal with distributed computing rather than in VM threads. So I'll show you some code in a second. I'll give you an idea of what this code is going to do. So this is our Vista example, our demo we like to use. It goes off to Flickr and it pulls a bunch of license plates. So we just do a query on Flickr and get back plates with American cars. We have a function that does image recognition, goes through the image and looks for the license plate in the image if it's there, extracts out and returns us the license plate number and the coordinates in the image where the plate is. We've got a second function which draws a box and highlights in the input image where that plate is. So I get this nice result out. And then a couple of the functions that will post to Twitter and Slack. So imagine I'm the police and I've got this camera set up looking for a stolen car, right? So it's watching cars go by. When it sees the one I want, it posts to my Twitter account. I'm a cop with Twitter, I don't know why, but my Twitter account goes off and says, hey, the car you're looking for is past this here. So that's kind of the idea, what it can do. So and just for your information, it's on GitHub. It's all there. It's written in Java and Go and Ruby, and it's a whole bunch of pieces. So in our world, you can have functions in different languages, and they don't care because they're just containers with protocol, right? So it's actually quite polyglot, this example. Looks like that, right? Go to Flickr, and there's a flow. So we get back a set of pictures, and then we iterate on those maps. So we actually fork off, or we run functions for each one of those images we get. That will then, once it's done, it'll do the draw function, and then it will actually do once it's finished drawing, it will actually post it to the two mediums here. Twitter, Slack. So the primitives we use, so we have FN flow feature invoke, start off, but then we use include feature API, primitives like then compose, so then compose this, you then do this, and when all of these to be done, and when it's all completed, we want to basically do some final cleanup task, perhaps issue a message in our case. So this is how I want to put these together, and we need to write code. So basically I have a function I write called a flow function that describes the algorithm. It says, call function A, call function B, call the scraper, call point detect, and draw, and this and that, and that's what I would write as a separate function, which is a controlling function, or a flow function. So here's the example. Now, I don't know how easy it is to see from the back, but this is just Java stuff, right? So get a flow, invoke the function scraper, and then compose. I have a lambda expression here saying take the results and take the results. And I'm going to invoke detect plates. And then I'm going to invoke the draw, and then I'm going to do both of these, all of invoke Twitter and Slack. And when all this is done, I want to come into this when complete and check that I have an error or am I okay, and do something accordingly. Something went wrong or it's great. Okay. So I've got this lets me describe complicated distributed programming algorithm. It's pretty easy to describe, pretty easy to understand. You can debug this in the debugger. When we're in the debugger, we don't fork things off across the internet. We run them in the local machine, but you still can debug these kind of things locally. So it's cool that both it works and it's debuggable. We have a experimental UI for understanding what's happening at runtime. So I can point this UI, or I can bring it up, and for each flow, so I actually have a single flow. So one flow function ran. It went off to Twitter, Slack, sorry, the scraper function here, each circle or each oval is a function. You'll see here we have a whole bunch of detect plates, so we had a whole bunch of images came by. And so even though the algorithm didn't necessarily make it obvious, we had we got a whole bunch of stuff happening in parallel. When the detect plates completed, it started up a draw function. You see sort of a snapshot of time. What you don't see in this image just off the page here, unfortunately, is if you go back to here and think about it, this describes a flow graph. There's a graph, there's a call graph in here. So what happens is we actually extract this call graph and we run this thing in the flow server. The flow server understands this algorithm, understands what jobs are being done now, it understands which functions are going to be called in the future. So normally in this UI, you'll see on the right-hand side functions that will be invoked eventually if things go right. So it's sort of a to-do list, right? So you'll see work essentially going from it will happen in the future to yeah, it's happening now and it's done until you've exhausted all your to-do list and you stop. Functions over. This UI is really cool. You can click on these ovals and it'll display the stack. So it'll display the stack if there's an error. You'll see the stack dump of what's happening in here. You'll also see the functions that got you there. So you sort of trace the path back to the root. You can actually see that in this debugger. So it's pretty cool. It's still experimental, but it's not bad. So it gives us an idea of the kinds of tools we can bring to understand this highly concurrent world we're going to be living in. So that's the control part. There's some really interesting subtle stuff that's going on here that I really want to point out to you. So Java 8 functions, all seen these, right? So we have a lambda expression, lambdas. Simple function here, it returns a string, or takes a string and returns string here, right? Takes a string and returns integer. Simple expression. Now what's interesting about this is it turns out that the lambdas are serializable. Okay, so this is a cast expression where we're saying we're declaring this function to take a string, return integer, and also implement serializable. Which means that I can take this lambda and I can basically schedule it. I can send it to my flow server that you saw at the top before, all those bubbles in that. That can become another unit of work that gets scheduled in our engine. It gets run at some point in time when it's necessary. So if I show you another example here of what that means, let me talk the lambda. Okay, so they're type safe. That's important, right? I compile that. I know the input-output, the lambda expression. If I just run a lambda by itself, I'm only paying for the compute required to run the lambda. It's cool. I can still test it in my debugger. Still runnable. So let me show you the example code. So here's a little function. There's no invoke function here, it's just a bunch of lambda. I have two expressions. So this thing takes a function takes an integer, doubles it, creates a string, and then returns that string as a result. So I've got two lambdas here. This one. If I'm running in flow, it will automatically take these lambdas, serialize them, and schedule them, and run them independently in one container, essentially. So what that means is, back to that sort of UI, if I run this piece of code, if you look in the flow UI, you would see three functions. The first function is the outer one, which is running, and then this is its own function, and that's a separate function. So I'm leveraging the distributed compute platform from within Java using lambdas in a very natural way. Now this would be silly. It'd be silly to have I times 2, because there's overhead and whatever, I would do that, but you can get the idea of why this is useful. There's one thing that's wrong with this, which is, you pay for use, right? So if you pay for when this runs and this runs, why in the world am I paying for this thing? And these numbers are clearly like my laptop type numbers. Why would I be writing my code so that I would have this function here who waits for the result of these two guys to provide a result, right? I'm paying for this thing, it's doing nothing. So once you start visualizing, you start to see the impact on what's really happening, right? So you don't think a lot about it. Oh yeah, this function here sits around waiting to get the end result, just return it. Do I need to return? Do I need to wait for the result? So if I wrote this code and did not accept the result, I just went and said, get X, double it, and create this string, and maybe it's update the database, whatever, the initial function is completed and gone. Right? So up there you can see it did its job, it forked off, or basically spawned off these other jobs, and then it quit. So my bill is lower, I'm paying less. So it's really interesting to be able to think about, how long your functions run, what work they do. It's really good to be able to visualize it because you don't want to be paying more than you have to. So it's not, in other words, this is nice Java, but there's some subtle things that can go wrong, right, when you're programming this model. But if you know what you're doing, you can take advantage of the platform. All right, so I think with those two things, I can write complex algorithms. I can actually schedule lambdas themselves. I can build pretty complicated applications on these kinds of FAS platforms. Last question is about latency and performance. And it came up right. You already saw when I ran that sample code, we had, the first time I ran it, it cost me a lot more than the second time when it was already running, right? So there is a cold start cost. If you're a FAS platform developer, we are obsessed with this. It's coming up all the time. Customers also are worried about this, like, I need to have low latency. The first time we call that function, it has the extra startup time. We want that reduced. We need to keep it small. You'll hear people who will write like a cron job to ping a function to keep it alive. Okay, so it doesn't do anything. It's like, you're alive. Yes, I'm alive. So they're kind of saying they want to burn CPU. They want, anyway, it happens. So, as you know, so FM running Java in container. Even if we weren't in container, we're in containers explicitly in Docker containers. Other platforms may use their own containerization technology to really run in containers of some sort. Or even small VMs. Even small VMs, if you have really small VM technology, same problem. You still need these things to be, A, respecting the constraints of the container you're in. You want to make sure that it was the case in Java that when Java asked how many CPUs there were, I can't remember the API, Git processors, or number processors, they answered incorrectly. It told you the host machine. So it doesn't understand it's running in Docker. So they make a lot of work to make the JVM understand the context of things inside containers. So there's that problem. We want to start fast. We want really small images. Okay, so you saw 400 meg, not so good. So in terms of the respecting this constraints and being friendly, there's a lot of work in the JVM, JDKT. So they're doing all kinds of things to make sure that things work correctly. This container metrics jump here is to deal with being able to understand the context. So apps can find out how much memory do I really have, how many CPUs or cores do I really have, so I can size my thread pools and do things appropriately. That's in 11.01. We replaced the earlier one, which was experimental, I think. This was just, it came out in 11. This no ops garbage collector. This is interesting. So it doesn't do anything. It's a no op garbage collector. It doesn't collect garbage, which if you think about it, if you have jobs that run for like 500 milliseconds and then die, maybe that's a good thing, right? So this could be useful. Unfortunately, every feature has like a good side and a bad side. I actually want my functions to stay alive, stay hot, so they boot fast. But if they're not going to boot fast, I want them to not waste time when they're running doing garbage collection because they're going to die soon. So like, it's a useful feature, but I'm not too sure where it fits exactly. It's experimental in a level. So there's a lot of work going on because the Java team knows that the future is containerized, right? So that's just reality. They have to run in container. So that's at that level for doing things. There are things you can use. Anyone using class data sharing? Yes, okay, the only person I've met so far. Okay, good. Apparently it's in the JDK since 2004. And one person in 30 or so is using it. It's simply a shared memory idea, right? So it's, all the things that I'm going to show you are all the same, essentially. Class data sharing, you can take the JDK classes and you can pre-compile, no, not pre-compile, you can pre-parse them. So normally when you boot the JVM, it's going to parse all these JDK classes. Every time it boots the JDK, it parses the JDK classes, right? JVM, sorry. So every time you do it, it's deterministically the same answer, right? It's always going to take the same bytecode and build the same in-memory objects. So you can take those, you can actually do a dump of the in-memory structure so that when you boot, it's faster. And you can actually share that between JVMs. So JVMs in the same host, even different containers, can share this pre-parsed core classes. I think it's about 18 meg when you do that. So you know I'm going to talk about image size, so I want images small and boot fast. This is a boot fast technique. This sort of hurts my small image size desire. So I'm having this tension between my goals. But that's there. App CDS is the same thing but for your classes. You can take your classes and have them pre-parsed so that again, you're not parsing them every time the bytecodes are being parsed and turn into objects every time you start your JVM. So you can save on your boot time. So it's a trade-off. It's a speed, more space on disk required for faster boot. You can use those features, and that's a nice feature. They also had some AOT. It's been experimental in 9 and 10. So fully, in this case, the AOT support was to compile, say, your application or your classes down to native code into a shared library, .so file, which then you could attach to the JVM. So it could partially, the JVM is still the same old hotspot JVM, but your code could be turned into machine code and just linked. So that could be nice savings. Faster start, all kinds of things. It's actually only experimental though, and I don't believe it has gone to production. Which is okay because it's something else we talk about that's kind of along the same line. Okay. So before I get started, let's talk about the image size thing. So why do I want small images? So imagine I've got this like hundreds of nodes and someone invokes a function and I say, okay, node 27, you need to run this function. It has to get the function container image over there. That's the first problem. So that function container image, if it's 27 meg, it's going to go over there at a certain speed. If it's 400 meg, it's going to take more. So I'm going to want to get that thing over there as fast as possible to respond to the customer's incoming request, right? The other thing is, Docker has a set up a lot of, does some setup. So it has copy on my caches, it has set up overlay FS. If you have a lot of layers, it slows down boot time because you've got to get all these layers basically sorted through. So the goal is small images with fewer layers is going to boot faster. It's a simple set of rules we want to try and go for. And so there's things we can do. We can use JLink, we can use smaller base images, and we can use Substrate VM from Graal project. Let's look at each of them. Right? So JLink, anyone using JLink? No? Okay. Okay. These guys back in headquarters are going to be like, everyone's using this thing. We worked for years on that. So the full JDK classes, 568 meg. If you use Java 9 modules and so on, well, the core classes are about 48. Is it 48? 46? I can't tell. It's too fuzzy. If you have a small, minimal, like Netty web server, it's about 60 meg. So with JLink, you can really shrink down your apps. That's good. Mark Reinhold was on the stage at Java 1 in the Java 1 keynote, demoing this, and he was focused on JLink and how cool it was. He wasn't really pointing out the really coolness, which was he took that Java application, which went from like 400 meg to about 27 meg in a container. So we had a 27 meg container, and I was like, in the audience was like, yeah, that's awesome. And he was like, oh, but JLink is so cool. And he sort of brushed off to the other part. No, the container part is the cool part. That's why you're doing this, because you want to get those small images, right? So JLink doesn't require you to use modules, but it helps, because if you don't, then it doesn't really know the boundaries, right? So it's going to go off and wander and do some static analysis. So you can shrink your app by throwing out classes you don't use. You can compress them, compress your whole app, but then the problem is you've moved decompression to runtime, and that'll slow down my boot, right? So again, I don't like this. I'd rather space time probably for that, not to use. You can also strip down the VM. I haven't tried this. You can strip down the VM even smaller by basically kicking out extra GCs. So there's a one compiler, one GC in there. There's something else it does too. It's a very small version of the JVM with minimal functionality. It should use case. I haven't tried that out. Small images. So if you're doing Docker now and you're using like Ubuntu or Debian, those are too big, right? So all you want for Java is enough operating system to run the JVM or run your Java app. So there's Project Portola, an OpenJDK project, to get Java running on Alpine with Muscle. So it's a libc replacement, and Alpine with that nice environment. It's a perfectly good environment, but because of the changes in JVM, because of Muscle, this is considered a port. So actually porting the JVM to this environment. So this is actually quite good because again, these images are 4, and this is only a few megabytes, 5 meg or something, or not 5, something very small. So this is a good idea, running on small images. So we can do that, right? So we can use this technique to get small images by running on small operating systems. And finally, for fast starts and small images, we can use Substrate VM. Anyone heard about the Graal VM? Yes? Okay, oh, a few, okay. It's German, right? So it's a good thing.
I have a question. Why do you move the whole image of the JVM on the network or whatever instead of just the relative code?
So why don't I move the whole image rather than just the application code?
Yes.
Yeah, so you're right. So if on a totally cold machine, I would have to move everything. Right, all the layers of that image have to go across that machine.
Why move images of containers at all? I mean, if you have on a new machine, if you have on a machine the JVM with all necessary driver and modules.
Yeah, so I could
move only the business code and no extra code.
That's not serverless.
Yeah. So
if you're assuming that you're the server that somebody has already put all of the things that you expect to be there, then that makes sense. Like, why do you have to send all this stuff? But
yeah,
you can't imagine that your function as a service vendor expects for all of the possible situations and all the variations of Java. So you're trying to strip it down to everything that's necessary to implement your code, assuming there's nothing there.
Now, so what you're saying though does happen. So once the container image is pulled and all the layers are pulled, that machine it's already got them. So next time, if I build 12 Java apps and they're only differing on one layer, the last layer, then yeah, I've got those on that machine. But I've got hundreds of machines. Those machines come and go, right? And often, for security reasons, we will be using in our world in Oracle Functions, we use VMs to manage the functions for a particular tenant, and when they're done, we just check it out. Like we just destroy the VM. We don't reuse machines, so there's this whole constant recycling in one way of configuration. So for security reasons, we don't want to leave anything lying around, right? So you get some benefit of it. The second and third functions will benefit, but the first one you still got to pay the cost. So that's okay because again, it's a problem, but we have strategies, right? So you'll see, especially when I'll demo Substrate for functions and this kind of thing. So with the Graal VM and Substrate VM, you can compile your Java app to a single executable. It starts to look just like a Go application, which is a binary and a garbage collector, right? Together, it's just native machine code for a given platform. There's no hotspot anymore. There's no garbage collector, obviously. It's smaller, has a smaller overhead in terms of runtime because It doesn't have compilers running, incremental compilers running, which means you don't have any of the caches they have. So there's tens and even hundreds of megs of cache that are used by hotspot that are not used by such a VM. It does have some issues. It's not perfect yet for all Java, so you can't run 100% of Java on this platform yet, because I think it's like 95% or something. And what's not covered is clear. They have limited support for reflection, and that's an issue for us, and I'll describe it. Because they look at the entry point for your code, and then you do a static analysis of all the call paths, right? They look at all the methods you can get to, classes you can get to, and they compile that, like the transitive closure, right, of that entry point, your main program, basically. So if your code loads something with reflection, it doesn't know. It's a string, right, that says, loads on class. So you can actually tell the compiler, hey, this class will be loaded dynamically. Please include it in my app, which is what we're going to see here. So this is all brand new. Let me show you the demo of what this can do. Now there's a pull request on the FN project that was filed on Monday, and I've got it. I'm demoing that, so I'm really on like the bleeding edge. I'm demoing the pull request. The Graal team has been working on support for FN for some time, and they were trying to get it ready for sort of release and get licensing approval, and then while they're doing that, we go and change our APIs, so that kind of makes life hard for them. Okay, so I'm not going to show you, but I should point out I've got a Kotlin function here. If you've got a Java virtual machine, it's really easy to run other JVM languages as functions. Kotlin's got support. You can run, buddy, David Daldassi blogged about Groovy. Someone just posted about Clojure. So JVM as the core is actually quite useful for polyglot support. Okay, I'm going to type a command to create a new function. I'm going to just run the script because it's long. It'll show you the function. Okay. So I run fn init image, fn project, then Java init, hello SVM. So I create a function called hello SVM. And we have, we're modularizing our CLI. So we're letting anyone write boilerplate generators. So we're saying init a function, and we call another container to just dump out the boilerplate code for us. Anyway, the SVM guys have given us an init package here that produces a function. And let's say hello SVM. It looks just like the other one you saw before, which is again, it's boring but good. I'll show you that. Okay. So we've got the same hello world function again. This is our code. Okay. Nothing exciting about that. One thing they do is they include a file for the compiler to tell the compiler that this function will be loaded, this class will be loaded dynamically, and this method is going to be invoked. So we can declare for the compiler static. We're going to need this thing, right? So you know the way that the FN works. You need to know this up front for the compiler. And what's different here is the func YAML file says the runtime is Docker. So since we deployed a Docker, as I said, we have built-in support for Java, Node, Ruby, and whatnot. But we give you the backdoor, which is just tell us it's Docker, and you can do whatever you like. Okay, so you can build a function using Docker, and that's the way they approach the solution. They generate a Docker file. So if you say the runtime is Docker, then we use a Docker file. They bring a Docker file that basically does what we do before for Java. We run Maven to get all the dependencies. We then look in here. Let's copy dependencies. Then we are copy across. Oh yeah, run Maven package. Sorry, there. So it runs Maven. So it gets the dependencies, runs Maven, and then they run the native image compiler. That's going to take that jar that's produced by the first build, the Java C build, and generate a binary out of that. And then they're going to package that binary up here. The binary is called FN, which is, I told them, is confusing. Because their name of their binary is the name of our command line utility. So I asked them to change that to something else, but they produce this binary, and they are going to invoke it. They're going to invoke their binary. and then you turn things around. So the entry point is that static piece of code, okay? So and the other thing that they're doing here is they're using from scratch. So they've got like almost no container. Like they've got just enough container to run the environment. That's all they need to use. Not even using Helpline. It seems to work out. So if I build this, let's see here. So if I do fn build again, I'll do the verbose. Maven build. Okay, so that's not fair because I've done this before in Docker Smart, right? So Docker has all these layers cached. So if you write code just like the other code, it's much faster. So let me break the code so you can see this thing do its trick. So let's put a space in here. Okay, so if I do it now, you can watch the actual compiler run. So, okay, the tests are running, Maven's running. Okay, so here's where it kicked in. So now it's running the native compiler. Again, I'm paying up front, right? I'm paying now for performance later. Rather than having Hotspot doing all this analysis and compilation over time, I'm having all this work done up front and doing static compilation. So this takes longer than the normal build. And I have my feeling is that if you're, I think we probably all see this, get to the point where we can build day-to-day with JVM, with Hotspot, and then for final production we could just basically shrink wrap everything and just call it, just use the new compiler. Right? So deploy that thing in there. And whether it's functions or not, this notion of hotspot for one sort of use case, and then perhaps static compilation for a final production of final. Okay, that ran, that took a little longer, right? Produced an image called hello SVM. So let's take a look at that. Docker image. Let's just grab that one there. 14 meg. Okay, so the last one was 400 and something, almost 4. This one's 14. I can do fn run this thing, local. All right, we'll check. Much the same as before. I can deploy it to the server. I local server. Berlin app, Berlin project, and local. Okay, so I do an fn. Oops. The Berlin application, I can say what are your functions. It's got 2 functions, the original one and the second one, and I can invoke either one, right? So fn invoke Berlin. So again, let's put a timer on this. So this is the cold start, right? So the first time it's called. Okay, so 640 milliseconds. Call it a second time. Of course, now it's running. If I look at the server, somewhere in here, I can see this hot function being started. So that substrate VM function is running. Oops. I can do the same thing with the other one. First time takes a while. Second time faster. So the start time for the original one here was more than a second for the non-precompile. And this one shaved off about 40%, so about 40% faster. And this is not really obviously not reality. This is like on my laptop with a use case of like simple hello world. But even at that, it's booting significantly faster. So 40% is nothing to see that. And if I run a world where I was shipping this image across the network, 14 meg is going to move really fast compared to 400. So it's pretty cool. Okay, so those are sort of like my criteria, like what would be good. I want plain old Java, I want to use whatever tools I feel like using, I want to build complex apps, I want this thing to run fast. I've got various options to use for low latency, high performance. It's a pretty good story, actually. It's not bad. It's not the same story it was, 3 years ago when Lambda launched. Use those other languages, right? So to summarize, I think that Java could be a top potential candidate for writing functions. Like we're using it for writing functions. I think that the barriers for using Java functions has come down. Certainly, our platform is very well suited for writing plain old Java. The JDKs has been improving to run in container. It all makes sense. having the ability to build complex apps and doing them with idiomatic Java. Right? So if you're a Java developer, writing complex apps in Java is much better than YAML. And having the raw VM, the substrate VM there for optimizing is a really interesting thing, right? So it solves a number of problems. It gives me fast boot time. It gives me low overhead, so low memory consumption, which is an issue because people tend to pay by how much memory their functions use. It runs fast, right? It's small, so it's small, so I move around the network quickly. So I solve a lot of the problems. So functional Java, I think I don't know why is it not the leading contender, right? Why is it not being used? So let me leave you with, you can try this yourself. This is all open source stuff. You can go to FN, you can go download the Java support, get the PR for Brawl, right? Download Brawl. Even if you need to download Brawl because it's in container images. It's all there. All these things we're doing are open for you to use, right? So you can try them out. So any further questions? Yes?
How do you log in a serverless world?
So how do you log in a serverless world? So what we are doing is capturing standard error. And you can define syslog URL. And at this point, you can stream them to wherever you want them to go. So all your containers can stream.
Right. So it's kind of vendor specific.
Yeah, it's vendor specific. Everyone pretty much captures standard error, and then how they do it is different. We're trying to take a open approach where we will have a sync for your logs that's just like there. But if you want to plug in something else, that should be possible. And that's kind of our strategy. Is it's a bit of a pluggable open source world. We don't want to plug everything. So you may have your favorite tools. Fine. So we were using not Peter, Page. No. I can't remember. Everyone counts it up on some cloud service. I'm using for this. Right? Define syslog in the output function. Set a property on the function, config, and then logs are streamed off. Yes.
Did I get it right that all your examples ran on a single machine on your laptop?
Yeah, so the code I was
Can you
showing is here.
distribute your code, your functions to several nodes? Is there a scheduler built into FN?
It's a good question. So there's a scheduler. So there's not a scheduler built into, well, there's a scheduler. Our architecture is we have the FN server, which is a single node, manages a single node, responsible for scheduling functions on that node. But then you may have multiple FN servers, so we scale out by having multiple of these control servers, right? And then we just load balance traffic between them. So when someone makes a request for a function, the load balancer will send that to a particular node, and then it will be scheduled locally. Now, that's how we do it. That load balancer, I didn't go into the details of FN, right? But the load balancer is smart. Again, this hot function idea we have, which is if you run a function on a given node, the load balancer knows you run that function recently on a given node. So if you have a subsequent request, it'll route that request to the hot node where the code is already available, rather than going to a cold node where it has to pay the startup cost. So that load balancer isn't necessary strictly. It's an optimization because it knows about the global sort of distribution of the functions that are working. But it's a very simple model. We just scale out by adding more and more nodes to this cluster and load balancing.
And you need to do that manually, or is there some logic into the
Right.
the load balancer as well?
No, load balancer, nothing, right now in FN, nothing is auto-scaling. So in the open source project, we haven't tried to address auto-scale. Like it's scalable, but knowing when to trigger that's something that's not in there. In the Oracle Functions Cloud Service, we've been building that for on the Oracle Cloud. So on the Oracle Cloud, it auto-scales. Of course, you also don't see the FN servers, you don't see load balancers, you see nothing, right? It's just a pane of glass. You just deploy your function, you call that, basically the same API. You do deploy, and you call it, and how it works is it's hidden, but we do have auto-scale to handle that inflection, that hockey stick inflection. We are looking at, well, one of the things is FN is not tied to Kubernetes, or it's not tied, or Swarm, or Mesos, any of the schedulers at that level. And we've so far resisted coupling ourselves, trying to remain independent. But as Kubernetes sort of takes over the world, we may be convinced that we should leverage their APIs. And then the question is, can we now tie into Kubernetes to leverage its capabilities to help us scale out, right? Trigger a scale up. So that's something that we're actively thinking about. Yeah, so today, if you were to run this yourself on-prem, you'd have to spin up some compute nodes, run some servers, put the load balancer in, and then you're kind of stuck with that until you triggered a scale.
More?
Because it's pizza.
I want to ask, what's being done behind the scenes to extract the lambdas that are used in Flow as separate functions and separate function
Yeah.
names?
So like I say, they're declared as they're serializable, right? So we know they're serializable. So when you see the API, jump back there, you see, that's almost it. Again, we'll just go back here. So over here, you're actually talking to our classes, right? So this F1 is this flow object, and then when you call it completed value, you get back a flow function, flow feature. You don't get back a plain old feature, you get one of our features. So we understand what's happening here. So we're actually taking that object, we're taking that and serializing it and sending it off. So it's because you're calling our API, we have control. So like I say, when you actually execute a flow function, it doesn't actually literally execute here. We actually are building an execution graph. We're building this workflow, wrong word, but a workflow, and passing it off to this engine and running it. So it's not exact, it looks like Java, it kind of works like Java, but it's a little bit different, right? We've broken up into a bunch of pieces and running those pieces separately and then tying them together. So imagine it's almost like having an RPC call here, right? Almost like that, and you can't see it, which is the beauty of the way we've done it, I think anyway, is it's natural.
You still say it works at runtime, right? Like you can debug this code. Like it doesn't just look like Java. You can debug it like Java.
Two things. Okay, yeah. So can I debug? So I can take this and run this in the debugger, and it won't fork off. I mentioned this. It doesn't run multiple jobs. So it lets you debug the logic.
Okay.
Right. So you can go to the debugger and put breakpoints and do the normal stuff. At runtime, we've got that. We have an API in the FM flow server, which we're using for that UI. Right. It lets us go in and look at. At this point, we're really just watching and we can examine the current state of the world. We can look at the state of the processes, who's scheduled, who's not, what's the stack, how do we get there. We can find these things out, but that's the extent of what I can do for now. I can't stop a running function. I can't, break it, right? It's actually like, if you think about it, it's a stack of functions. So I kind of want to stop one. So far, we're not that far. So we're not that clever. Like, we're clever, but not we've only been at this for a little while, right? So there's more work to do.
You do have to be careful though, because when you talk about serializing your content, you're essentially serializing your context of the Lambda function, which if it's large, serialization isn't particularly small, so you might be passing over the wire a huge context.
Currently, this is the case, yes, and no one likes Java serialization, especially the Java team and stuff, right? This is but it actually works, right? So this is no big deal. Even the ones we saw where I'm saying do some computation, it depends on how big it is. But yeah, you don't want it to be massive.
And you're probably on a local network with a fast network, so it's not a huge deal.
Yeah, but still, you still don't want it to be going crazy because this could kill you. So again, even though it looks good, you still need to know stuff. You still need to know how it works. And that graph that shows you the execution saying this is running for this long, understanding, why is that running so long, doesn't make sense. You kind of need to get there, and that's the more advanced understanding. But the primitives are easy to use. So I like this idea that it's easy to use for new people, but power users can do complicated things. It's kind of one of the principles. This can look easy and it can do massively complicated stuff, but it could be also dangerous, right? That's one good point for the newbie. Yes, sir. Sorry.
Where are you actually sending that number to? Are you creating a new Docker container for that, or is there a generic Docker container that handles all the numbers?
No, so we need the Java classes for this, right? So we actually so if we have a Docker container that contains this program, we're taking the same image that contains this program you run, and we're just running this code in that context. So we need all those Java classes available to us to run the Lambda. Which makes the point that Substrate is not compatible with Flow, because Substrate doesn't let us do all this clever running Lambdas in another context. But no, we need all these classes, so we're actually using the same container image as the host function and executing that Lambda in that space because we have all the Java classes we need. Right versions, right everything, right? It's the same world. So we're just basically almost like we're We're saying, just, this is the main program. That's all it runs. That makes sense.
How does it work if the same function is called concurrently? Is it
We don't do that. So we do allow concurrent invocations, but they will result in two functions. So these are not reentrant. These are not called twice, not at the same time. Right, so at least currently we do not do this. So if you call a function twice, we will spin up two containers.
okay?
If you have a bunch of calls coming in, so you have a certain number of containers that are being spun up, and we have some controls over, how many you should run at the same time. If one becomes free, it returns a result, it's now can accept another request. So we can give it another invocation.
Okay, so
Do
every container is single threaded.
single. So the model, again, part of the goal here is to have a simplified programming model that lets us do this massive scale.
So
There is some discussion of should we allow a function to handle multiple concurrent requests, and then you get into complexity. What about complexity for the developer? Oh my God, am I leaking state across implications? I mean, it's a trade-off.
sure. So my question was actually they cannot share some resources.
Share resources. Technically, yes. So this is kind of like the standard hack, which is create a static. I know. Everyone cringed when I say it. But people do this. They create a static, and they'll stick a database connection in the static. Right? So they come into the program, they create the static, or the static gets initialized, they connect the database, it sits there. As long as that function is alive, and it's accepting subsequent requests, right? It's single-threaded, one at a time. Technically, it's going to work. But at some point, if it's idle, it'll go down. Right? It'll go down and be gone. Then when it comes back up again, if you create a new one, it's going to have to create a connection again. So people do stick statics for handling external resources that are expensive to allocate. I don't know if it's a good idea. It's done quite commonly. So it's real. It's but it is possible because if the same JVM is running, which it is, then statics can persist. I've thought of using some stuff in Substrate VM. In Substrate, they'll let you invoke code and have isolated, basically a separate class loader, right? So they can do this sort of easily. They can firewall off invocations of each one to make sure that they don't leak. So I could put in functionality to allow concurrent, but firewall off all the concurrent invocations. So there's a lot of things I can play with. We're trying to figure out what's the optimal density and usage, right? So this is not all totally clear yet.
Yeah, well, I would say one question or two, and then, because pizza's getting a little bit cold, so. Feel free to ask later.
For the sake of the pizza.
Yeah.
I just thought, right before you talked about the static types you can use, it's all about using just final variable and two methods shared.
Well, if it's just a JVM, so you can use all the tricks that you can do in persist state. But again, I don't know if that's necessarily a good idea. So like I've been talking to the database guys. This is the big thing: database connection. So Oracle database connection startup time is long. MySQL guys say we're good. You can create a connection, tear it down fast. We're fast. That's our whole use case. So different technologies have different characteristics, and that might be suitable for functions and or less suitable. But best not to hold a resource. Okay, we're done. Thank you.
Yeah, I mean, free to ask them, but thanks a lot for coming.
Thank you.